Okay, cool. I'm Schwartz, and this is Preetam Jinka, and we're from Cortex. We're a database monitoring software as a service platform. It's the best way to see what your databases are doing in production. We support MySQL, MongoDB, Postgres, and Redis at the moment. We're working on some more. This is our contact information. We'll show that later as well. So this is a journey, the story of our journey of selecting representative samples of data from large streams of rich and complex data. We did it wrong for a while. Well, wrong is a subjective term, but we did it in a way that didn't meet our needs and had some really bad side effects for us for a while. It's complicated, it's confusing. So we'll talk about what we used to do and the things that we tried as we started to find a better way to do that, what worked and what didn't, and what we've ended up with. So we won't dig a lot into the historical realms of what we used to do, but just suffice to say that we used to use an equation essentially that said now we should sample an event, and it didn't work very well. It had all kinds of bad side effects and consequences. Okay, so we'll dig right into this. For us, we're monitoring queries arriving at your database servers, being serviced, and then leaving again. We're going to use the term event so that we're not specifically talking about our use case exactly. I will show you how this works into our use case. But this applies generally, it would apply to log data or HTTP requests or all sorts of kinds of things where you might want to sample from a stream of events. So in this diagram, the little yellow dots represent events, and they flow from left to right as time flows. And there's this stream of them, and they're arriving, in clusters. And what we want to do is measure the workload. So this is, as Brendan mentioned, workload characterization. This is a workload characterization tool here that we're, at least as part of our product, is about workload characterization. So what we want to do is help you understand what work your servers are doing. So there's this very high velocity stream of queries arriving and completing on your server. And this is instrumented in little agents that run on your database server, so it's very performance constrained and it needs to be very fast and efficient. So there's a bunch of constraints there. So first of all, the stream of queries or events itself is way too high velocity. We're software as a service. So if we were measuring and transmitting, and storing, and analyzing all of those in our platform, we would be taking, let's say, 20,000 queries per second off of your database server and shipping them up to the cloud, and that's just way too much. So the first thing that we do is we categorize these things into buckets of time. Our metrics resolution is 1 second granularity. So we're measuring things generating metrics about the stream of events, and then there's a clock tick every second, and we accumulate the metrics every second. And then that condensed stream of data is what we actually send back to our APIs. And it's multi-dimensional, so it's not like one, here I'm showing one little chart to represent the metrics about this stream of data, but it's actually multi-dimensional. There's lots and lots of different kinds of things that we measure about these queries. So there's way too many of them, and we're just turning into once per second metrics. So now we have these metrics, but metrics are not enough because now we've thrown away most of the interesting and useful information, and we really want that information. So if it's SQL queries on a database server, we want illustrative examples of the individual SQL. We want to know the user, the database, the latency, the exact timestamp, the origin host, and most of all, the SQL. Because if you find a query that's performing badly or something like that, you need a real example of it with full literals and everything included so that you can inspect it, run explain, et cetera, and figure out what you want to do to improve that. So if you just have metrics, it's impossible to do a lot of really important and useful things. And this again applies to lots of different kinds of use cases like logs and so forth. Imagine if you were just aggregating your logs into metrics and then you didn't know anything about the individual log entries. So we want these events not to be completely thrown away. We want representative samples of the events. And it turns out to be very hard to do this. So that's what this talk is all about. And representative is very important. If we don't pick events from the stream as samples in a representative way, then we will lose interesting patterns as well. So this is a real screenshot from an older version of our application where we found there was a query that was increasing in latency and then suddenly getting fast and then slowly getting slow again. And without representative samples, we would not have been able to see this picture clearly. So there's lots and lots of reasons that you want representative stuff to keep the important patterns in your data. The event streams are much more diverse and complex than I had shown before, and that's part of what makes this hard and interesting. We typically have many hundreds of types of queries that are running against a database server. In some applications, we may have hundreds of thousands or even tens of millions. So the workload can be extremely complex and varied. Here I'm representing it with a handful, 5 different colors. You can see some of them are bigger than others, some of them are little, some of them are high frequency, some of them are sparse. So there's all these kind of different dimensions along which these categories of events vary. And one of the interesting challenges is in keeping the representative nature of the sample and balancing a whole set of trade-offs and goals around that. So some of our goals are to sample enough events so that when you zoom into a particular category of events and look for samples, you have some. At least once an hour is kind of our goal, often much more than that, but not too much. We'll talk about that too. We also know that some events are more important than others. For example, a query that returned from the server to the client with an error or a warning is more important and interesting. So we want to prioritize those. We also want to avoid taking samples of things that might have, for example, personally identifiable information that the customer doesn't want us to transmit to our APIs. There's lots and lots of these kinds of things that we have to balance. Some of them are customer driven, like the privacy concerns, and some of them are technical or platform driven, like the goal of not flooding our APIs with a whole bunch of load. So some of these goals conflict, and that's part of where this becomes interesting. For example, biasing towards towards taking samples of queries that are important for some reason, such as having errors or warnings, conflicts with rate limiting those. There's a couple of other things. One of the big ones is correctness versus efficiency, because again, this has to be extremely low overhead. It's running on high load servers in high traffic situations. We need to do this in a way that doesn't cause CPU consumption or memory consumption, and we track that over the long term. We have lots and lots of metrics about our agent's performance itself. So Preetam did most of the implementation of this, so I'm going to let him take over from here and talk about the specifics of the statistics and the implementation.
Thank you, Darren. So there's lots of different approaches to take when you're sampling events from a stream. I guess the simplest one would be to sample one and n events. So you would just have the stream and you'd have the counter that decrements after each event, and once it hits 0, you'd sample it and then you start over. There's also other ways you could do this. You could separate your time intervals, and basically for each interval you can pick maybe the worst event. So maybe in our case it could be a query that has the highest latency. You could also pick one randomly, but the issue is these methods aren't really good at capturing a representative sample. And what we want is basically a representative, regular stream of samples coming from all of the events that are coming through. So whenever, so I'm a math student, and whenever somebody says events with a regular mean or average rate, I automatically think Poisson distribution or Poisson process. And whenever you look up sampling events online, you'll usually see somebody mention Poisson process. So a Poisson process is basically a process that has the characteristics where each event is independent of the other events in the process, and the time between events is exponentially distributed. So if you were to use an exponential distribution, to calculate the probability of sampling. So basically what you would have to do is every time you see an event, you calculate a probability of sampling it. And based on a random number you generate, you either sample it or you don't. And if you use the exponential distribution to calculate that probability, what you would end up with at the end is something that resembles a Poisson process. So in each case, we use the time since we last saw an event to calculate that probability. So we actually use a simpler approach. What we want is not a Poisson process, and I'll get into the details shortly, but we do something very simple. So every time we see an event, we look at the time since the last time we saw an event for that category, and then we just we use a simple linear equation to just figure out that probability. So what we end up with is something that looks like that plot. So every time we see an event, we use a simple linear equation to figure out what the probability is, and then use that to determine whether we sample that event or not. So to explain this a little better with an analogy, I like to think about buses at a bus stop. So imagine you're at a bus stop, and the only thing you know is that buses arrive every 5 minutes. So when you show up to the bus stop and you're waiting for a bus, you expect to wait 5 minutes because, I mean, that's all you know. But suppose somebody told you that a bus showed up 2 minutes ago, or just left 2 minutes ago. Now, intuitively, you would think that you would expect to wait 3 more minutes because the average time between buses is 5 minutes. So that's the behavior that we want. But what if I told you that it actually doesn't matter when the last bus left? You still have to wait 5 minutes. So that's the approach you would take if you were using an exponential distribution. And that's because the exponential or Poisson process assumes that the occurrence of events is independent. But when you think about buses at a bus stop, they're coming at a regular schedule, and that's not actually the case. So if you don't understand this still, just find us in the hallway. We'll explain it. But yeah, don't use the exponential distribution if you want regular sampling like we do. So there are other reasons why we don't use the exponential distribution. So if you plot the exponential distribution and the CDF of the normal or uniform distribution, you'll see that at lower values, they are approximately the same. So you won't immediately notice a difference, but once you deal with larger time intervals or larger time ranges between events, you'll see a big difference. So the thing about the exponential distribution is that, so suppose you're expecting samples once an hour, but what if you have an event from a category that only shows up once an hour? If you use the exponential distribution at that 1 hour time range, the probability of sampling is significantly under 1. It's around 60% or so. So what if I told you you have this rare event that comes once an hour, and you want to sample it approximately once an hour, but you only do that 60% of the time. So that's not a reasonable method of sampling. So using the uniform distribution with just a linear equation is actually more reliable in rare scenarios. It's less computationally expensive. It's really simple, and it's easier to understand. If I told you about, a Poisson process and independent events, it gets really confusing. But the simpler way is actually the better way in this case. So there is a gotcha. We actually made this mistake, and it's a very subtle mistake, but it actually has a huge impact on how samples get selected. So I mentioned that what we use to calculate the probability is the time since the last event. Now that's a really subtle distinction to make. So basically there's the last time you sampled an event coming from the stream, and then there's the last time you saw an event coming from the stream. So it turns out if you use the last time you actually selected a sample from the stream, you'll actually end up oversampling, and it has a really bad effect because you end up with way higher sampling rates than you would expect. So in this case, what the effect is if you use the time since you last sampled, you'll get events in between the next time you sample, and the probabilities basically add up, and they add up very quickly. So what we had was a scenario where we used the wrong value in our code, and the sampling rate was extremely high, and the math didn't make sense, and there was a lot of time that was spent on this. And basically the only change was we had to change the variable like last sample to last seen, and that fixed it. So code reviews are good. So I mentioned that we were using the last time we saw an event per category. So that's an efficiency issue because, as Baron mentioned, we have lots of categories. In some cases, we have millions of categories to keep track of. And what that means is for every one of those categories, we have to keep track of the last time we saw an event coming from that category. So in the beginning, what we did was we had LRU. And what the LRU does is it keeps a maximum number of events or categories and keeps track of the last seen time for each category. But the issue with the LRU is if you have an edge case where you have just significantly more categories than what your LRU can hold, and they're all sort of coming at the same time, you end up with like a category churn, as we call it, where things are cycling through the LRU really frequently, and basically because things get dropped off the LRU, we actually forget them, and we end up with lots of oversampling because we assume that we see new categories all the time. So what we needed was an efficient solution to keep track of the last seen event, or the last seen timestamp for each event, with potentially lots of categories. So we decided to come up with a sketch. So sketch is a probabilistic data structure that trades off accuracy for CPU usage or space. So in our case, we wanted to support lots of categories without using lots of RAM, because these things run on our agents. They have to be very, very lightweight. So if you've heard of a Bloom filter, this is sort of the same approach. In fact, there are some sketches which are basically the equivalent of a Bloom filter. So the sketch we invented was inspired by another sketch called the count min sketch. So the count min sketch basically approximates the number of times you've seen something, and instead of using the counts or frequency, we use the timestamps. So we call it the last seen sketch, and it's very compact and efficient, and even though it's approximate, it does return false results sometimes. But what ends up happening is those collisions are actually in our benefit. So this is what it looks like. It's really simple. It's basically an array of arrays, and each array has a different length. So what happens is for each category, we hash the category into an ID, which is just a number. And for each number, we take the modulus of number and the size of the array to figure out the location in each of the arrays. So with 4 arrays, there are 4 cells that a category maps into.
Our real sketch is much larger than this, by the way.
Yes. So in reality, our arrays are on the order of a few thousand cells. So for example, consider we have a category that hashes to 20, and we're storing the timestamp 8. So in this case, it will hash to the indices 2, 0, 0, and 2. So for each cell, when we're updating the last seen timestamp, we set each cell to 8. And again, when we're looking up a value to see when we last saw a category, we look at all the cells that it hashes into, and then we basically get a list of timestamps. And what we do is we pick the lowest timestamp because basically if you have different timestamps, it's because different categories are hashing into the same location, and there you get collisions. So if you pick the lowest timestamp, it is the lowest possible timestamp that the query or event category would have been seen. This could be higher than the true value, but because we're using the timestamps to calculate probabilities, and if it's a shorter time range, we actually get a lower probability of sampling. It's actually in our favor to have collisions because we'll sample less frequently instead of more frequently. And to put it all together, I'm going to give it back to Baron, who's going to summarize what we use the sketch for.
So our sampling capabilities are pretty sophisticated. There's a lot of different kinds of filters. Samples, events are considered to be eligible or ineligible for sampling based on things like the text of the SQL, various other kinds of things. There's a lot of capabilities we've built around this to do things like guarantee that we can audit queries of interest, or guarantee that we won't capture samples of things that are private, those kinds of things. So there's this whole filter of stuff that we built in our agents to determine whether something is eligible for sampling or not, and if it is, then based on some other things such as whether the query had a warning or so forth, whether it's important, and we bias the sampling towards important events as well. So given that, if it's eligible and the potential bias, then we look in our sketch, try to find the last timestamp that we likely saw this category of query or event, and compute from that a probability which we compare against a random number generator to determine whether we should select that sample or not. So the combination of all of these things put together gives us very nice representative sampling, and it achieves our goals with regards to biasing towards things that are more important and rate limiting things, both individually per category as well as global rate limiting. So now let's return to our earlier picture. We have these really high frequency metrics that describe the overall shape and so forth of the event streams. And then we have the individual samples of events from within those streams that we can use to further inspect the real data, the source data. So that's the best of both worlds. That's what we want. Actually, the best of all worlds will be when we add histograms, which we will add in the future. So the rate limits, there's still a few things to consider with regards to rate limits. Again, we want to avoid flooding ourselves with this enormous amount of data in case there are edge cases, and there are always edge cases. Our customers' workloads are incredibly diverse, sometimes even within a single server, but certainly across the entire span of all of our customers. There are many different kinds of workloads. So there's a few things that might happen. For example, if we're trying to sample from each category of events once per hour, and you have 10 million categories of events, and that's a lot of samples per hour that we would be taking. So we have a global rate limit, as well as the goal of sampling each category of events. The way that's implemented right now is with a quota that just decrements to 0 as it's used up per time range, and then it resets. This is very simple. I think probably in the future, when we have an occasion to take another look at this, we'll probably vary our per category sampling rate based on an exponentially weighted moving average, because the quota that winds down to 0 can cause starvation in some categories when there are sort of abusers or heavyweights in other categories. In general, it's still, we've investigated tons and tons and tons of scenarios, and it still works pretty well, but this is kind of a theoretical case where we'd like to improve in the future. And then, of course, not all of these events are created equal. So, we found a lot of extremely rare incidents in production systems this way, including in vendor code. For example, there was one customer who was using a vendor system that would, once in a million, would throw an error on a query. And we captured this and brought it to their attention, and because we were able to sample those individual events with higher probability, we actually captured the 1 in a million that caused the 1 in a million error. It was setting a variable, it was for a MySQL user, setting a variable to a negative value that can't take a negative value. So of course, sent that back to them, they sent it to their vendor, the vendor fixed it. It was one of those kinds of things that you will never see in staging or development. This is a mature product, it's not new. So this problem has been in production in lots and lots of their customer systems for a really long time, and we were able to find it. So the bias towards important events is actually extremely important for this kind of thing. I think we're saying important too many times, but if we were just sampling from something that happened once in a million times and we didn't bias towards these events that generated warnings or errors, we would catch that there were, because we have metrics about the number of warnings and errors per category of queries, but we wouldn't catch the individual example, and so we've never been able to figure out that somebody was trying to decrement something negative. So just a couple of screenshots to kind of show how this all fits together for us. Here is a chart of a metric of warnings in a category of queries, and you can see that it's 0.001% level of warnings are generated in this category of query. So, what is that, 1 in 100,000 or something like that are generating warnings. But over the last whatever time range we're looking at there, I think it's 3 hours, we have 23 of them, 23 occurrences. So when we drill into this query in our user interface, we actually get a user interface that shows a scatter plot of the samples as circles. Time goes from left to right, latency goes from top to bottom, and you can click on those circles in our user interface, and then in the area below, we get to see the exact text of the event, we see the user, the database, the latency, the timestamp, all of those kinds of things. And I've circled where it says warnings 1. That's something that we extract from the network protocol. And so we can get these individual examples and look at them. This is something that's in our own backend. It's not a concern because it's trying to, remind myself, it's like create table if not exists. In MySQL, if the table exists, nothing happens, but the command, the response from the server to the client does say that there was a warning, and if you look at what that warning was, then you'll see, table already existed. So it's not a concern in our own backend, but for a lot of scenarios, it might be a real concern. So I'll show you one of those next, where in just large distributed systems, things get really bizarre, and rare errors fly right under your radar. So this is from one of our MongoDB users. There were queries that were returning with errors all the time, and but only in specific circumstances, which we were able to pull out. So looking at that, I've circled the error number. If you look up in the MongoDB documentation, that is that the query is not allowed to, the query would do a scan of that entire collection, touching too many documents in the collection. So MongoDB refused to run the query and returned it back to the client with an error. And the reason for that was, so this seems to be like the problem, right? There were lots and lots of queries returning with errors in this customer server, and one of them was create index, which had a typo in it. So it was actually a syntax error. It was like, I don't know, create index or something. And MongoDB was also returning errors. So this collection had no index where it was expected to. And I think one of the interesting things about this, we find this in all types of products, we're not bashing MongoDB here, is that these really rare errors will occur in production situations. Unless you have production visibility into the real network traffic, you don't find them. It's very hard for developers to reliably catch and log and then get visibility into these kinds of errors. I think we've all probably seen the if no error, do this without the else clause to log the error, right? So that's basically what was happening here. So that brings us almost to the end of our time. I think we have 1 or 2 minutes for questions. Happy to take those. Happy to talk about this stuff, any level of detail in the halls.